All right, thank you very much. And so the talk I'm going to present here is a somewhat impressionistic talk of a work in progress, which is a joint project with Baptiste about the contingency of space-time itself. Now, all of you, or most of you, have probably seen this very slide beforehand. It's the general suggestion that's supposed to be illustrated here that we find in quantum theories of gravity that space-time itself, as we know it from GR anyway, or something closely related to that, is not what's fundamentally there according to quantum theories of gravity. Rather, we have some other structure which then gives rise, in some sense, to some approximation under auspicious circumstances to the kind of space-time that we believe to inhabit. In a way, it's just going to be parallel to, there are things like tables and chairs in the world. Those things are clearly not in the fundamental ontology of any physical theory, but they seem to exist in the actual world. Of course, there's something else, some sort of material degrees of freedom, whatever exactly they are, which are what's fundamentally there, and they give rise at the emergent level to tables and chairs. Now it seems straightforward to think that the world could have been such that these fundamental degrees of freedom, matter degrees of freedom, do not combine such as to form tables and chairs. There's a sense in which tables and chairs are metaphysically contingent. It requires a certain specific arrangement or collective behavior of the fundamental degrees of freedom such that there exist tables and chairs. Now, if that picture is supposed to be analogous to that, then you might think that space-time itself may not be necessary. It may be metaphysically contingent in a way that is analogous to the way in which tables and chairs are metaphysically contingent.
Can I ask you a question real quick? Do you mean to say metaphysically or physically?
Metaphysically. I'm going to get to...
They're also physically contingent, right?
So, yes, I'm going to say a little bit more about that. I mean, what kind of necessity or modality really we're going to mean, I'm going to specify, I think, on the very next slide. So please be a little bit patient with me. Anyway, that's the question, that space-time is similarly contingent, or is it necessary to physical reality, or maybe metaphysical reality?
Space-time is a pseudo-Riemann manifold, or is else?
I don't want to be quite as specific as that. Probably it could be something slightly different, but something like that, yes. Something like the kind of thing that as we find it in GR.
Yeah.
Yeah. Or maybe a closely enough related theory to that. Okay. Our thesis is going to be that space-time does exist contingently. The reason why Baptiste and I thought about this and sat down to work this out a little bit more is because I've said somewhat nonchalantly things like, space-time exists contingently in front of an audience of metaphysicians who then would all raise their hands and say, like, what do you mean? And this is not, this is outrageous and this and that and whatever, they think like, all sorts of objections. So I thought like, okay, I need to sit down, or we need to sit down and sort of think this through a little bit more carefully. But that's the thesis we're going to defend. For that, we choose a naturalistic approach to possibility. So let me say a little bit more about the possibility or modality that I envision here. And the naturalistic ansatz we're going to use here is the idea that we should look to physical possibilities as licensed by our best physical theories. So in that sense, we're really not going to be very much interested in a much wider sense of metaphysical possibility. So let's narrow it down to physical possibility, as licensed by our best physics. The idea is something like that a theory T of physics licenses a physical possibility just in case the possible world is consistent with the laws of that theory. So simply put, we could say we could use the models of this theory as a guide to what is physically possible according to that theory. Now, maybe, in front of this audience, that seems a pretty boring, straightforward thing to say, but I do think there is some, philosophical substance in this sort of defending that kind of position. Because, among many things that we bracket, it raises many non-trivial questions about the relationship between models and worlds. All of this is going to be left for another day. I also leave for another day some problematic considerations about the modal asymmetry, perhaps, that we have between physics and other sciences and different levels of scientific descriptions and so on and so forth. So there's going to be a lot of interesting, deep, substantive questions that I just bracket here. I'm going to use the following principle then in this general methodological approach that I will say a state of affairs is naturalistically possible just in case it is a model of a theory of our best physics. That's still very rough, it's not very precise, because I would have to say what is our best theory, our best physics, of course, and there may be some debate about that. But before I do that, actually, I meant to make reference to a paper that's currently being written by Sam Baptiste and James Reed, where they identify the physical possibilities by trusting the solution space of effective theories in their domain of accuracy. So you have a relativization, in a sense, to a domain of accuracy. And what we propose here is certainly meant to be compatible with that idea. Here, of course, an effective theory is understood as the best possible description within a specific domain. So in a sense, it's a somewhat wider conception than you may find it in quantum field theory, perhaps. Now, we need to say what we mean by best physics, because otherwise that's a very sort of somewhat empty template. So we need to be saying more about that. And because we're going to be interested in spacetime in particular, I'm going to say that for spacetime, GR is the best theory we have. That's the best physics.
When you
Yes.
say best possible description within a specific domain, what is that? Is it the domain of accuracy that you mentioned earlier, or what defines that specific domain?
That's a very good question. So it's like it's starting from the phenomenology in a way, from the way the world manifests itself to us. We delimit a range of phenomena that we try to understand, and then within that specific domain, a particular theory may turn out to be the best description, which, if you think of it like, high energy physicists do, then it's going to be a range, an energy range at which, your theory is going to be an extremely good approximation, and then at some scale it will lose its property of being a very good approximation, and so on and so forth. Okay, so we're going to have the non-fundamental theory, which GR is going to be, that's going to be GR, with the non-fundamental space-time, and some sort of fundamental theory of quantum gravity with its entities or structures it postulates. And there will be the very interesting sort of metaphysical project. What exactly is that relation going to be? Is it going to be a relation of emergence, grounding, determination, relative fundamentality, ontological dependence, necessitation, reduction? These are all going to be different relations, and I think there's much more to be said about that, but I'm going to bracket that. That's not really the project for today. I hope it's good enough for you to come with me to the next slide. pick your favorite relation here, and then let's move to the next slide. Okay? So at the non-fundamental level, we have GR and a sort of a space of GR models. By that I mean there's going to be a set of GR models, and there's going to be some relations between some of these different models, and that spans, in a sense, a space. Not a physical space, of course, more like a modal space, a space of possibility. And these, the elements of that space are going to be like the models of space-time. Fundamentally, we're going to have a space of the models of our theory of quantum gravity. There's going to be models there as well, and they're going to form some space in a very abstract sense as well. Now, you already see that I have sort of indicated subspaces of these space. And by these subspaces, I mean to express the idea that some of the GR models are going to be non-quantum gravity GR models. That is going to be those sort of relativistic spacetimes which are not going to approximate in any way the fundamental quantum gravity things. So maybe if you're doing causal set theory, it's going to be those sort of spacetimes which are causally so pathological that they're just not going to be described in any useful sense, to any useful approximation by any fundamental causal set. So there will be some, in general, you should not expect that the fundamental theory is going to be giving rise to all the very, very many GR models we have. Conversely, it's also not going to be the case, however, that all of the models of the fundamental theory are going to give rise to relativistic spacetimes. They're not going to be related by whatever your favorite relation you picked on the previous slide to a relativistic spacetime. Some of them may be highly non-spatio-temporal, so if you think of, to just give you one example, for instance, in a group field theoretic approach that Daniele Oriti has been developing in recent years, and collaborators, of course, it's going to be the case that a system could be in a state such that it's not in a geometric phase. In that sense, you know, that state, in that situation, it's not going to give rise to space-time, anything like the GR. So they're going to be non-GR quantum gravity models. All right. Then there's the relationship between those things which do give rise to those things in these subspaces. But today, the important thing is going to be that there's also going to be things, you know, models of this, in general, of these theories outside of that subspace. Some of these are going to be non-space-time models. All right. So that's the sort of models you should be scared about, which is why it has this ragged orange, you know, boundary.
Just to follow you, if I may, in a quantum, forget relativity, in a quantum theory, what do you mean by model? The classical theory understands the solution equation of motion, but in a quantum theory, what do you mean by model?
Well, it's gonna be.
For a quantum particle.
Sorry?
For a quantum relativistic particle, for a qubit, what is a model of a qubit?
So it's just going to be a possible state of affairs according to that theory. So there, if it's a non-relativistic quantum mechanical theory of particles, it's going to have some particles, and it's going to attribute to these particles properties, some properties and some combinations of properties and correlations between properties, and evolution of these properties as they are permitted by the Schrödinger equation, as they are sort of, you know, specified by the theory. And any way in which, you know, according to the theory these things could be, that's going to be a model of that theory. Okay. Now, maybe you just think, you know, oh, this is obviously true. This is obviously going to be the case. But there's some ways to resist the conclusion that it means that there's a sense in which it's naturalistically possible that space-time could not have been. One objection, or the objection would be something like the following line. You could say that the modal structure which is assumed in the fundamental theory, that is, the models licensed by the fundamental theory, the possibilities according to that theory, has no ontological teeth, to speak somewhat metaphorically, meaning that we should not take this seriously. It's not really the case that those non-actualized models of the fundamental theory are real possibilities. We shouldn't be misled by that. Maybe we're just being some sort of anti-realists about them. Maybe these are just mathematical devices that help us better understand the actual world, but they're not in any real sense possibilities. So you deflate these theoretical possibilities as some sort of surplus structure that's useful, maybe has some instrumental value, and so on and so forth. Why would you do that? Well, there could be different ways, different justifications for that. One could be a sort of a form of fatalism. You would say that, well, these counterfactual fundamental possibilities, these models, do not correspond to physical possibilities because the world could not have been at the fundamental level different from what it is. It has to be that way. Now, the response here that we would like to give is to say, like, well, if you accept the contingency at the emergent level, you accept that the world could have been different in the sense that it could have not contained tables and chairs or something like that, it seems somewhat inconsistent to then say that you shouldn't also accept that same plurality of possibilities at the fundamental level. Now, fatalism at the fundamental level, to be coherent, therefore, ought to be complemented, it seems, by a fatalism at the emergent level. So there's a sense in which you would then have to say the world could not have been differently from the way it is, including at the emergent level. So it's not true that tables and chairs could not have existed. And then, that's what we really, mean by fatalism. And if that's what you want to be, then yes, of course, at that point we will not have a counter-argument against you. If you want to be a thoroughgoing fatalist like that, then you can resist our view. But full-blown fatalism like that has not been a very popular position in philosophy for a while. So that's you're standing with the minority there. Anyway. Maybe there's another, somewhat more sophisticated and to our mind more interesting motivation for the same objection, and it's what you could call the sort of actualist response. You could say like, no, I'm not a fatalist. Of course, the world could have been different from what it is, but I still want to make that objection. And my motivation is, as I said, a form of actualism. And the idea is that the only sort of physical possibilities that we permit is internal to the actual world. So the way in which this is supposed to work is that a state is physically possible just in case it's compossible with another state of reference and a proper part of the actual world. So this, tables and chairs may be contingent in the sense that there are parts of the actual world which do not contain, significant parts that don't contain tables and chairs. Maybe I would say it's possible if I were to hit, the window with a rock, it would break. That's underwritten as a real possibility, even though in the actual world nobody throws a rock at that particular window, because on other occasions in the actual world, in relevantly similar situations, rocks have been thrown at windows and the windows did break, and therefore that is what licensed the modality there. So if we're going to the fundamental theory of quantum gravity, we're going way too far. to admit all sorts of really weird possibilities, and we shouldn't do that. We should be much more restricted in our admitting of possibilities. So the idea would then be the non-spatial temporal models of the fundamental theory of quantum gravity. They are not describing the actual world, because the actual world, however, it is actually structured, fundamentally speaking, is one in which we have space and time, in which we know. Sorry?
Is it everywhere?
I'm going to get to that point, but the idea as well, I mean, of course it is, because GR, and that's why GR is such a good theory for many parts of our actual world, because to an extremely good approximation, it is like that. It's been, this is established, unless you're a really extreme skeptic of I don't know what kind. Anyway, but the non-spatial temporal models, the non-geometric modes of group field theory or what have you, these sort of things, they do not correspond to real possibilities because they're so remote. They're clearly not in any way what we find in the actual world.
So when you say remote, you mean that there's no empirical evidence for them? Is that what you're basing your actual versus remote?
Yeah, no, that's a very good and subtle question. There may be empirical evidence in the sense of that we find ultimately, hopefully, for our quantum theory of gravity, some empirical evidence which says like, oh, this is the correct theory of quantum gravity. And we have reasons to believe that, and it may therefore, in that theory, be the case that there are some models which are non-spatial temporal. Mm-hmm. So, in that sense, that's already, dangerous to the actualists. You're going too far. Mm-hmm. No, you shouldn't have that kind of evidence. You need something more than that. You need, in addition, some sort of reason, presumably empirically based reason to think that this is really the way things could have been in the actual world, not just a model of our theory which as such has been empirically confirmed. Now it's a very delicate distinction, because if you just go to GR, in GR this is, for a philosopher it's interesting, for a physicist it's a frustrating situation. There's so many models, and so many of them seem so crazy that physicists go like, oh, no. Many of these models are, they're not physically reasonable. The world, this is not relevant, right? And the philosopher go like, that's interesting. When we do LIGO, or we observe Sagittarius A star and find that our black hole models are actually very good models, and we do GPS corrections using GR and all of that, we find evidence supporting GR, and GR predicts that these are models, right? Maybe crazy models, but they're models. So how do you distinguish that? What is actually sort of really licensed by the evidence is going to be a highly non-trivial and interesting question. But the idea would have to be that in order for there to be some sort of empirical evidence, there needs to be a bit more than just evidence for a theory, which may be extremely permissive in that sense. But the problem is the following for the actualist. It seems as if we have very good reasons to think that the very, very early universe is a part of the actual world in which quantum gravity should come into its full, bloom, as it were, which is, where we should confirm it, which is going to be a part in some sense, and I'm saying not a phase or a period, because that's sort of the temporal speaking, but it's a part of our actual world, it seems, which is going to be highly non-GR-like. It's going to be something which is going to be wildly different from what GR does, which is a very good part of the reason why we think we need a quantum theory of gravity, precisely because GR does not succeed in giving us a good description of that part of the actual world. So if that is a part of the actual world, it may very well be that that part of the actual world is non-spatial temporal in some sense. So if by the actualist logic you accept parts of the actual world as ways in which things can be, then it seems as if, nevertheless, space-time is contingent. It could have been that space-time does not exist. So we should accept on that thinking that a proper part of our actual world is not spatial-temporal. Okay, now of course you could accept that, but you could say that, yes, I accept that it's physically possible or naturalistically possible that part of our world is non-spatial temporal, but what I do not accept is that our world is completely non-spatial temporal. That of course would still be okay. Good. Now I was thinking of going through some examples to make these points vivid, but I realized that I probably don't need to do that or not spend too much time introducing causal set theory once again. So let me just go to the relevant question here in causal set theory. What are the conditions under which we do have, given a causal set, we do have an emergent space-time? Now, as we've heard this morning, causal set theory is a work in progress. We don't have the final theory yet, of course, but maybe there's going to be some sort of list of conditions like that. It seems as if the causal sets have to be sufficiently large. We need to add some sort of dynamical rules or some additional constraints on the partial orders, because otherwise we're befallen by the KR catastrophe. We find that most of the causal sets in a mathematically precise sense are not approximated by, don't have a continuum approximation, as we've heard this morning. So there need to be some additional constraints which rule out these sort of things. They have to be manifold-like. They should be well approximated by some sort of relativistic space-time, it seems, or at least that they could be in some sense. Maybe they should even be, related in some way to some narrower class of space-times. And that approximation should be approximately unique. Moreover, so this is the Hauptvermutung, the main conjecture, or fundamental conjecture on your slides, I forgot. Main conjecture?
Fundamental.
From a fundamental conjecture, yes, yeah. And then, of course, all of this is classical, so we should actually come up with a quantum version of the theory, and that should give rise in some generic sense, perhaps, or at least under sufficiently auspicious circumstances, to classical space-time states or something like that. Some list like that. That may not be the final list. I'm not really interested in negotiating each individual point on here. Maybe, we could, delete one and replace one of these conditions by something else. That would be fine. The point is this, however, there are going to be some sort of conditions which are going to give us the kind of models of causal set theory that we should think are the sort of models of the theory at the end of the day, right? And even if you meet the relevant conditions, generically we should expect that there will be some models which don't give rise exactly to relativistic spacetimes. So if that's right, then it would be naturalistically possible that spacetime does not exist. I think that similar things follow if you go to loop quantum gravity and sort of study the basic laws of loop quantum gravity and the ways in which you can have, spin networks or spin foams. They could combine following the laws of quantum gravity, loop quantum gravity, in ways as to not give rise to relativistic spacetimes. Okay. Good. So I hope, and I'm going to skip that. I already talked about loop quantum gravity, group field theory. All right, let me spend the last, how many minutes?
You're about 30 minutes down.
Ooh, okay. The last very few minutes with thinking a little bit, which is going to be an important part of our project is to sort of think through now the implications. If that thesis is true, what are the implications of that, of the contingency of space-time? And we think it certainly has implications, for instance, for the debate between relationalism and substantivalism. It's going to have implications for both of these positions. The question that we're asking is, how does the contingent emergence of space-time now affect that debate? And I'm going to warn you, this is work in progress, so I'm really soliciting, your objections and or maybe additional, strengthening of our points on this. It's somewhat tentative. First, for relationalists, it seems that perhaps relationalists get the easier, less sort of problematic consequences than the substantivalists. If you think that relationalists are those who think that space-time ontologically depends on matter, but not the other way around. So there's space-time and there's matter things or physical objects, and what we disagree about in the relationalism versus substantivalism debate is which one of them is sort of ontologically prior or depends on the other.
Means that, sorry, but is the other way around, not the vice versa true? So relationists think that you can't have space-time without matter, right?
Yes.
But do they think you can have matter without space-time?
Yeah, not necessarily, yeah.
That's traditional relationism.
Maybe not, but it's not so much that's, it may not be traditional. I agree it's actually not traditional relationalism for the reason that everybody's sort of agreed that space-time is metaphysically or physically necessary. And if that's the case, then you don't need to worry about the vice versa part. But now it's going to be irrelevant. And we're here going to assume that the relationalist is not committed to the vice versa thing. That for them, it seems prima facie possible that there could be matter without there being space-time. Okay, and it seems as if, because of that, they're in a better position to accommodate the contingency of space-time. If space-time is physically contingent, then it seems as if something could exist in its absence. There are ways in which the world could have been where there's no space-time, but there's something else. Now the question is, what is this something else? Is this really matter? Is it quasi-matter? Does matter, the concept of matter, have in itself sort of necessarily spatial-temporal implications, as Descartes thought, who thought of matter as res extensa? It's characterized essentially by being spatially extended. Now, if that's your conceptualization of matter, what we have in these other cases is not going to be matter. It's going to be something else. So the relationalist will have to give us an answer to this. What do we have there?
Is there anybody who's a relationist in that sense?
Sorry?
Is there anybody who's a relationist in that sense?
No, I don't think so, because this is new territory. We're sort of trying to... The very first line?
Is there anybody who's a relation in that sense?
You mean, is this question also about the parenthetical remark or about the rest?
About not the parenthetical remark. I never understood relation in that sense. I don't know anybody who thinks that space-time ontologically depends on matter.
So you don't know any relationalists?
Nick Huggett's a relationalist in this sense. You would know better.
So...
This one is a relationalist who never think that space-time
I mean,
depends on matter.
I think this really comes from the traditional
Yes.
Leibnizian conception.
Yeah.
And there's a claim that maybe this doesn't even make sense to talk about in geometry.
Yeah.
Like when we talk about like math-dependence relation, that makes sense for the way Leibniz frames it.
Sorry, I think this is all very interesting, but let's maybe save it for Q&A.
Yes, so I grant that there are different conceptions of relationalism. It's certainly something that has been defended, I think, by Jill North or something in the vicinity anyway, of thinking in terms of grounding or dependence as what's going on in that debate. But there may be other conceptions, and it's clear that a relationalist is going to have problems with, matter, gravitational degrees of freedom in GR with, gravitational waves and stuff like that. Yes. So this is a slide I skipped. Okay. And so there's still going to be, even if you manage to survive this contingency of space, and there's going to be the challenge that you will have to come up with some account of what's going on with vacuum spacetimes. Because presumably the vacuum spacetimes of GR, or at least some of them, are going to be among those models we will want to recover from the fundamental theory of quantum gravity, precisely because it's actually the vacuum models of GR which do a lot of the empirical work. A lot of empirical confirmations are concerned with vacuum models, such as, famously the gravitational wave ones, very importantly. So I don't think you can really justify at the level of GR eliminating all vacuum spacetimes. That seems crazy. So if that's true, then it's going to be, we have this sort of interesting problem perhaps for the relationalist that there's some fundamental degrees of freedom which are quasi-matter, which nevertheless give rise to vacuum spacetimes or something like this. So how do you deal with that? That's going to be an interesting problem, I think, for the relationalists. And if I can get 2 more minutes, or we did start late.
We started 10 minutes late, so we're going to
Okay. Let me try to wrap this up. For substantivalism, I think there are some severe problems that are going to have to be addressed. And here, I assume that for substantivalists, matter ontologically depends on space-time in the sense that there couldn't have been matter without space-time. Again, that's maybe a conception of substantivalism that you want to resist or that you reject, but if you think with Jill North in terms of ontological dependence or grounding as what's going on in the debate between the two, something like this is going to have to be the case for the substantivalist. If that's so, then the existence of matter necessitates that of space-time, because matter couldn't exist without space-time existing. That's what it means to ontologically depend on that. Consequently, the non-spatial temporal quantum gravity models better contain no matter, because there's no space-time there. How can you guarantee that? How can you make sure a priori that whatever you have fundamentally, these fundamental degrees of freedom are not in any way matter degrees of freedom, but they would have to be on your account. And there's perhaps a tempting strategy for a substantivalist to say like, but like many other things which exist and are independent substances, they may be emergent, so space-time may be emergent, I'm still going to stick to my substantivalism. So this is what we call emergent substantivalism, and they face the challenge of explaining how a substance like space-time can be contingent. If space-time is a substance that exists independently of the entities that occupy it, then it seems as if to have its own intrinsic properties should determine its nature, and it's therefore difficult to see how space-time could be contingent. So how can space-time be contingent, as its nature would seem to be determined by these intrinsic properties rather than by the relations it bears to other things? Much of this is work in progress, as I said, and much more thought needs to be going into sort of spelling out all these consequences. But what's a big motivation for our project is to try and figure out exactly how debates, in particular this debate, is going to be affected by the thesis if that space-time may not be necessary, but may be contingent. So last slide. in our naturalistic approach to metaphysics, we use our best physics as a guide to physical possibility. And in this spirit, if we now take seriously the space of possibilities as suggested by theories of quantum gravity, then the conclusion that space-time is contingent is hard to avoid, it seems. And that's not just, I mean, this is, you know, in any of the theories of quantum gravity that I've looked at anyway, that seems to be the case. That seems to have implications, at least, for long-standing old debates between substantivalists and relationalists, and we're interested in working these implications out. And it also serves as a starting point for an exploration of the nature of the connection between the fundamental and non-fundamental structure. Thank you very much.
Okay, and now we have some comments from Niels Linnemann.
Okay, yeah, that works as well.
So you need other slides.
Yeah.
Where are they? This?
Yeah, exactly. Yeah, thanks a lot for having me. So maybe one way to say thank you to Baptiste and Chris is to comment on their work. Not sure why this is on Spacetime, is Spacetime contingent, but I think that might have been a title at some point. Okay. The plan for this quick comment is as follows. I just want to first zoom out again. What is, so to speak, the setup for the criticism of Chris and Baptiste of substantivalism and relationalism, and then zoom in from general logical considerations via analytical metaphysical considerations into naturalistic metaphysical considerations. So yeah, just as a starter, substantivalism, at least as I have learned about it, is typically the view that space-time is primitive, fundamental, yeah, you can spell this out in more detail, and then relationalism is the view, yeah, that space-time is derivative from matter, and so naturally there's a third way that you have emergent space-time that's at least outlined like this by Martens, that's space-time is derivative from something else. It's one way to set up the whole context. Some people are looking skeptical, maybe. Okay, good. Now what you can do, you can play around by combining options, so to speak. You can have the option of space-time being primitive / fundamental, or not being so, and meta being primitive or fundamental or not being so, right? And then, for instance, in the top left corner, you get dual substantivalism, so both matter and space-time are fundamental, right? And where it gets really interesting for us here is the scenario where space-time is derivative. We can distinguish once more between the scenario where space and matter are ontologically independent, and then the negation of it. And here, so to speak, is where the meat is for us. So we have relationalism there, but also three versions of emergent space-time. Very interesting for us that we can make a distinction depending on how strong our notion of matter is. We have two scenarios from this logical considerations with emergent spacetime with no primitive matter. That's a scenario where you have emergence of both spacetime and matter together, or the scenario of a kind of super substantivalist spacetime emerging and then getting matter in a way derivative from that. Or on the other spectrum, other side of the spectrum, you have the scenario of emergent spacetime together with primitive matter is a kind of dualist scenario again. So you have, rather than dualist substantivalism, you have emergent spacetime plus matter. Okay, so now we get from this logical considerations to the analytical metaphysical consideration, which involves thinking about harder what we mean by fundamental, primitive, derivative, and so on and so forth. So in the talk, I think the notions of ontological independence is used heavily to characterize relationalism and substantivalism. Then I think also, at least in that section of the talk, one kind of equates ontological independence to existential independence. But then we can just make the general warning that this is a dangerous way to spell out the ultimate goal of fundamentality / notion of fundamental. So X is less fundamental than Y, is not necessarily well captured by existentially dependent on y, but not y on x. So just as a slight warning, but I think one can spell this out, and I think the interest of you and Baptiste wasn't even to go into detail there at that point. So maybe this is not such an interesting criticism. So I don't mean it as a criticism, just as a compliment, so to speak. But now then really move to the things which are of interest to us here. That is the naturalistic metaphysical considerations. It also became clear throughout the talk. Of course, I want to know what is meant by space-time, what's meant by matter. And this gets informed from looking at different theories, across the board. From that we get maybe high-level criteria, which are less framework-specific, like a split structure role between space and time, or an ordering structure / role, which is part of space-time or spatial-temporal structure. We can also have more framework-specific notions of space-time or spatial-temporal aspects, like Lorentzian metric, conformal structure, what have you. What's interesting here is that the selection criteria for space-time matter, as we get it from the naturalistic discussions, don't need to match well with ontological criteria. So if you just take the recent discussions of Martens and Lehmkuhl, this is just one of their papers of how to characterize matter via the space-time. You see a lot of criteria which actually make matter depend on space-time structure. So for instance, energy traditionally depends on some form of background symmetry as a notion. Kinetic criteria they have depend on some form of causal structure. And then of course you, in this conflict, right? Are these selection criteria we get from practice simply not good ontological criteria? They should be dismissed for that reason. Or is it actually, after all, that matter, for instance, in this case here, is not to be seen as ontologically dependent? So we have to make this decision between what is really done in practice and what do we want for our metaphysics. So it's not so easy to say we can really read out the metaphysics from practice. So going naturalistic is not a unique path, so to speak, right? It involves metaphysical wishes and discussions. Now we really get to my comments labeled A, B, and C. So depending on if you spell out what you mean by space-time and what you mean by matter, then first observation, this shouldn't be a surprise to Chris that I bring this up, is that space-time contingency already arises across models of GR. So what I mean by this, well, for at least a certain school of thinking of what space-time is, and then the functional school of Knox, or also the dynamic approach school, arguably, yeah, space-time in GR is not just this G, or it's not simply G by fiat or so, but G only in a certain relationship to other matter fields, a certain coupling relationship, can fulfill roles such as that of inertial structure, of chronogeometric structure, and so on and so forth. Meaning, the law of GR scenarios provide you allow for a sufficiently rich matter sector, which still contain matter, but don't make G spacetime. Okay, so in a way you get this problem of matter already there, and similarly, just from the very notion of what you mean by spacetime as being dependent on other matter fields coupling to it, you get a notion of spacetime which is not exhausted by intrinsic properties. So yeah, you also get this problem of emergent spacetime in a way here. Similar with the GR relationalist thing, is the relationalist really better off provided everything else is matter here? Well, the question is there in such a scenario of GR where you have this functionalist understanding of the metric field a la Knox, is it really the case that there's only matter, but for instance, to think of the manifold structure, etc. pp. That can be discussed. So we have some time, I think?
Yeah, maybe a couple more minutes.
Okay, good. Second comment, this is the condition one before turned around. Depending on the notion of matter, that also tacitly of spacetime, concept theory does seem to include some form of matter. So there's a whole subfield of Q of T in causal set theory, so to speak. I got briefed on this a bit more yesterday night. So at least one has managed already to put scalar fields on causal sets. One is working on more, and one hopes that only technical obstacles are right now in one's way, and so there's no conceptual obstacle to get through with this project. And so yeah, assuming we don't want to make matter, the notion of matter hostage to the notion of spacetime, why not say that causal set theory has then matter, provided that this project gets sufficiently far? But then, consequently, provided that causal set theory allows for matter, you may also want to rethink the status of space-time causal set theory, right? Because if you already have matter on the causal set, so to speak, the causal set can play more roles than formally ascribed, and so maybe there's at least a room for a sort of quasi-space-time substantivalism here that could be discussed. Similarly, I think one needs to go into details with other proposals, group field theory, string theory, loop and gravity, and so on and so forth. And the last comment is a bit of a cheap one, I think. It just refers to what we generally mean by naturalist metaphysics. I mean, depending on our epistemic standards, maybe we can only do sensible natural metaphysics at relative levels of reality in certain effective regimes to begin with. What do I mean by that? This is final theory objection under McKinsey, which basically draws on that we will never, most likely at least, get to a final theory of physics. Therefore, we only do metaphysics or natural metaphysics with physics which is not done yet. But the problem with metaphysical claims is they're very sensitive to theory changes. They're very much dependent on specific formalism. And so what we should really do could be a proposal to reply to this kind of meta-inductive skepticism is to just do metaphysics scale / regime / level relative. So in that sense, I don't really understand why we could not continue with the project of discussing substantivalism, relationalism, just in the regime of GR and only in that regime. I mean, we do the same thing for Newtonian gravity, right? And so on and so forth. And as a matter of fact, we can still have some of these discussions Chris and Baptiste discussed about contingency, but then maybe in the context of, say, Alan Knox program or dynamic approach program, what have you. Of course, you might have some other response on how to address Mackenzie's final theory challenge, but this is, I think, something for another day. Thank you.
Okay, questions? Start with Sumati and everyone else get your hands up.
Okay. So, I want to understand this definition. So I like the idea of this contingent, what you call it, space-time is contingent on something that, it's what we think of as emergent in physics, that things have to get together. Like, it's not enough to have just the atoms, but the way in which they come together to produce. And that's sort of the effective models of looking at condensed matter systems. You don't look at things necessarily just at the quantum mechanics level. You put them together, and then there's new physics that emerges at different scales. And I think that's how the quantum theory of gravity will have the right theory, which should have those structures. But what I don't understand is your definition of surplus structure, because, I mean, if I looked at fluid dynamics and I looked at fluid dynamics and I'd say, well, that's going to be my guide, I would, I think, never come to the theory of atomic. I mean, there'd be too much structure, surplus structure in the atomic or molecular level that would never express itself in, but it's essential in this what is it, contingency plan, right? It's essential, because without that you wouldn't, the theory requires all that structure to then assemble and then come together and then do all of these things. So starting from the sort of high level of, what is physically accessible, say you didn't have experiments that said anything about atomic structure, which you were. I mean, and that's unfortunately the state we're in right now. We don't have the empiricists, we don't have enough empirical information. But presumably, if the theory is a good one, then that surplus information finds its way or becomes, necessary, and could become necessary in ways that we can't even imagine. And just to sort of state that in a slightly, in something that's rooted in the continuum, even if you wanted to do continuum quantum gravity, in the sense of the path integral, we have GR, but we also need, if we did the path integral, we'd have space-times that are not solutions, which do not minimize or extremize the action, just as we do in quantum mechanics of free particle. And those are important. Those give you that, without them you don't have a theory of, you just have the classical theory. So the things that are quote unquote off shell, the things that of course, these very, very strongly different models of space-time, they're off shell. But to me, of course, the proof of the pudding is in the eating, like finally, what can you deliver with these theories? But I don't think that can be a fundamental objection. So it can't be a fundamental objection that there's surplus structure. And so I just want to, put that there.
Oh.
I have some other comments, but I'll wait till later.
Did you think that our argument depended on saying that, the fact that there is surplus structure in quantum gravitational theory is a problem? Or
Okay, so maybe I misunderstood. I thought that was a criticism of it, or that. You use some words.
No.
Yeah.
I completely agree that this is to be expected.
Yeah.
I wouldn't
in the
wanna-
sense of the actual world, so there sort of seems to be a contradiction. But if you, yeah.
Oh,
okay.
I
Alright.
see.
What guides this sort of surface structure and so on?
So I don't think that that's a problem, or I didn't mean to assert that this surplus structure is sort of idle and completely useless. I certainly completely agree with your view that, in fact, this is hopefully going to give us some interesting implications, which eventually will show itself in some empirically testable way. So I did not mean to assert that this is not the case. I think this was coming up in the context of the actualist objection to our thesis,
Okay.
that on their view, we depart or accept as physical possibilities only those sort of things which are part of the actual world, or we have reasonable evidence for that it could be part of the actual world or something like that. And it seems, or that was the idea, that these non-spatio-temporal modes or states or models are not part of the actual world, and therefore they're not real physical possibilities. They're just sort of surplus in the sense that they tend to show up in the theory, but we shouldn't in any way endow them with any physical significance. So that was the objector to our position. It was not the position I meant to endorse.
So I think I made a, okay.
Yes, so I completely agree with you, and there's all these good reasons to resist this actualist response and to actually take, sort of physical possibilities in those, maybe funny-looking models, this really unexpected surplus structure, to take that seriously.
Right.
I mean, part of my career is also, I've worked as, interpreting GR and trying to argue that, physicists, even the very best, physicists tend to dismiss space-times of relativity as pathological, but maybe we have to be careful here. Maybe this is like a new prediction, some surplus structure of GR that we might discover, that perhaps the best models are non-globally hyperbolic and of all sorts of funny properties. Just in the way that Einstein and many physicists at the time thought the singularities are like this, the end of the theory itself. So shouldn't endow that with any physical significance, the models which are singular. But it turns out that, well, in a way, they pointed us, they predicted phenomena, exactly those singular models, which are extremely important and for which now, in some sense, Nobel Prizes have been awarded. So to rule out any singular spacetime as unphysical would have been a huge mistake. And maybe, it could be a mistake at the level of GR to rule out other classes of spacetimes. This is a tricky business of what to rule out. No, And of course, it's all the more so at the fundamental level. So these may be crazy, counterintuitive, a priori bizarre, models of surplus structure may exactly be the sort of things that, with a really ingenious, experimental setup, it might be our key to see quantum gravity at work. Yes.
First, just think what prizes you win when you build a time machine.
Sorry, what?
When you build a time machine,
Yes.
what prize you'll win? The Nobel Prize. We can go back and take all the old Nobel Prizes. Anyway, I want to see if I understand something here by way of an analogy. In Newtonian mechanics, someone might say, well, there's a certain space-time structure, there are particles, they have certain properties.
Mm-hmm.
But if we don't include the dynamical laws, we can come up with all sorts of possibilities,
Mm-hmm.
all sorts of crazy-sounding worlds.
Mm-hmm.
Now, let's say the dynamical laws, we can still get some crazy worlds, but fewer of them. Worlds with tables and chairs, we have no place to sit and eat dinner and stuff like that. It would be crazy. Okay, now to the causal loop theory. What you have basically are the elements, the fundamental events, and a partial ordering relationship on them.
Mm-hmm.
And you're pointing out that there are ways of arranging these such that you can get spacetimes or not get spacetimes. But I'm not clear now about where the laws come into the story.
Good. Yeah. So, that's an excellent question. It's not one for which I think it's in my job description to answer at the end of the day. It's, the physicists have to, fully articulate these theories and tell us what the laws are of their theories. And it's pretty clear that, what's sometimes called the kinematic models of causal set theory are not going to be the end of the story for the reasons we heard this morning. So there needs to be more. My point is that if you look at ways in which physicists working in different research programs in quantum gravity deal with this and the somewhat tentative conclusions they've reached so far, it seems as if even once we're done specifying these additional conditions or additional laws, we should in general expect that some of the models of these theories are not going to look like or give rise to relativistic spacetimes.
So, what do you think about giving rise to whatever the arena is, its dimensionality, or whether it's quantum mechanical? So, are those going to be contingent also?
What do you mean by the dimensionality? Like the dimensionality of physical space? Or?
Yeah, there'll be some physical space. It might not be GR space, but some arena. And the arena will have a dimensionality. And maybe it'll be 1,000 dimensions.
That's not obvious.
I can answer that right off.
Okay.
Those are possible contingencies too, right?
Yes, so the dimensionality is certainly a possible contingency, absolutely. Because there is a question of what the dimensionality is, or what the arenas are. And there's going to be some arena in some very, very general sense, not to be confused with physical space at all, but some arena that has to be specified at the kinematic level, perhaps, of a theory. The theory tells us, look, we start with building blocks like, the causal set elements, or, spin networks, or something like that, and we build up, in some general way, a huge array of possible ways that things could be, and then we add additional or impose additional conditions. So yes, in that very general sense, there has to be an arena, but there's no reason to think that that arena is going to be connected in any direct way to physical space.
What about it being quantum mechanical? Maybe the laws
So,
you need to get our space-time out, something that our world emerges from, will make it the case that anything you get will be quantum mechanical.
So there is certainly the general expectation that the fundamental theory that we're going to end up with in quantum gravity is a quantum theory. I mean, in a way, that's the point of the research program. What does that mean? Well, it doesn't mean that we have space and time and the Schrödinger evolution, of course. You know, it must be a more general understanding of what a quantum theory is. There should be something like an H bar in there. You know, probably we're going to have some Hilbert space or you know, Fock space or some sort of state space like that has the flavor of a quantum theory. We will have some algebra of observables defined, and you know, some at the much more abstract level there will be it should be a quantum theory. I do not see how even fixing that part makes space-time non-contingent, because that has a priori nothing to do with, you know, the existence of space-time.
Seems that way.
Yeah.
I mean, would you say that if there are phases in your theory in which space-time is emergent, then that's contingency? So if you
Yes,
have-
because
you
there
have
exist phases in which you know, which are non-geometric, like in the, you know, the group field theoretic approach. You have non-geometric phases. So there's ways in which the fundamental system, whatever exactly it is, you know, the structure, the fundamental degrees of freedom could be in such a state as not to be, you know, geometric phase.
Chris, try to be useful here, not critical. But since you said it's work in progress, let me
Yes,
point
please, be useful.
So first of all, I couldn't agree more with your main thesis, right? Space-time, in the sense you say is contingent, and it's not realistic possible that space-time, in the sense you say, it doesn't exist. I mean, you know me, so I can put it on a T-shirt.
Yeah, maybe we should print
So,
T-shirts like the one Perry has.
Yeah,
you know.
exactly. Space-time is contingent. I think I'll do that. I want to put a little but, which is mostly to do with the last part of what you say, but also with the thesis itself and with all the metaphysician as you started raising your hands. Which is, you've been a little bit cavalier about what you mean by space-time. I asked you explicitly, and you said, oh, something like GR. Okay? But then it seems to me you're meaning exactly this space-time of GR. You know, I mean, it's a continuous four-dimensional manifold. Blah, blah, blah. Now, why I'm saying that? Because space-time is a heavy space, and time and space-time are very heavily loaded words with all sorts of uses and meanings which go in all directions. And nobody has put rules on how to use them yet. So there are two directions in which this same words are used. And I think if you don't keep this in mind, there's certain confusion. One, which in a sense is the less interesting, is that people talk about space-time much before Newton or Einstein or general relativity. And if you think about space and time as were conceived by Aristotle or Leibniz or also people in between, it's nothing to do with a four-dimensional continuous or a three-dimensional continuous plus one, it's completely something else. So why I'm saying that? Because in the wildest model, as you say, of quantum gravity, there are aspects which are spatial or temporal in some very generic sense. So somebody could say, no, come on, there is space in sense that, okay? In causal sense theory, of course there's space-time, this is space-time. Or in
places, right? There's places.
There are places, there's localization, there's a contiguity, there's all sorts of things which are traditionally attached to space, always there, it's still there.
Right.
Now, the other one is more specific, is that in most theories of quantum gravity, one way or the other, let me put it this way, forget gravity, is Maxwell electromagnetic field contingent according to our best theories, forget gravity? No, because Maxwell electromagnetic field describe continuous electromagnetic and there's quantum mechanics, so there are situations in which the quantum properties are explicit and do not describe that. But nobody uses this language. Everybody says, no, in our world there is an electromagnetic field, it has quantum properties. That's what people say. So what I'm saying is, if I have a pendulum and describe it classically, I say this is a pendulum which has this equation, q double dot is equal minus omega q. But then you say, oh, actually, I make precise measurement is quantum mechanics, so it has quanta, which is, okay. I don't say there's not the pendulum anymore. I say there's a pendulum, but it doesn't behave according as thought before the classical theory. It's a quantum pendulum. It's a pendulum that behaves quantum mechanics. So in the language of a lot of people, the thing that replaces quantum space-time in the sense you say is still called quantum. It's still, sorry.
Yeah.
The thing that replaces classical space-time in the sense space-time in the sense is still called space-time. I would call a state formed by a spin network space-time. It's just quantum, and I would call the causal set space-time. It's just quantum space, not space-time. Now, why this is important and it's relevant? It's not just terminology, because when you discuss, for instance, the relevance of all of this wilderness of the quantum gravity, what replaced with for substantivalism, for instance, okay, you say, okay, matter necessitates space-time to exist according to a substantivalist, but now there is no space-time anymore. It's not that there's no space-time anymore, it's just space-time is more complicated in that case. So I can still be a substantivalist like before. Instead of sitting on a continuous manifold, my fields sit on a discrete thing, or on a quantized thing, or on a...
Okay.
Just an invitation.
Good, thank you. That is very helpful. Thank you very much. Okay, there's different points in there. It's a fair question to ask what I mean by space-time. And I mean something much more narrow than space-time, is identified with any structure which has, in some remote, very general sense, something like spatial or temporal things in it in some very remote sense. I would want to exclude that, because then pretty much anything is going to qualify, because surely we expect the fundamental structures of quantum gravity to have some aspects of that. They're not going to be completely non-spatial and completely non-temporal. They may be, in some sense fundamentally non-spatial, like causal sets, but more like temporal, or they may be more spatial and less temporal, and there may be different ways in which the fundamental structures look like. But of course they're going to have some aspects of that, because otherwise it would be a real mystery how something like a general relativistic spacetime would be a good approximation to some of these structures. So I don't want to be that inclusive. We do want to say, no, spacetime is a more restricted sort of thing. On the other hand, it strikes me as, I did assume for the purposes of the talk here that spacetime is what GR tells us it is. And that may be a somewhat, overly narrow view. I'm prepared to relax that a bit, because perhaps, we'll discover tomorrow that although we thought so far that GR is the best theory of space-time, we might find tomorrow, because we do some new experiments or have some new observations, that some correction of GR, but still a theory like GR, similar to GR in that it's a sort of a space-time theory. It's clear how it relates to like Newtonian space-times and sort of pre-theoretic notions of space-time perhaps, or space-time as it features in our phenomenology or something like that. It's still, but it's not GR. It's maybe the sort of things that Niels may have had in mind, that sort of alternative views of GR. It's the ways in which GR relativistic. So sorry, GR spacetimes may be contingent already at that level. So it's not as if that theory is a more fundamental theory, but it's rather a theory that replaces GR. I mean, so maybe this is just sort of a logical possibilities, because I think actually the wiggle room to come up with a theory at that same scales as GR, that's as successful or better than GR, it's going to be really, really difficult. That I don't think there's all that much methodological freedom. But I want to accept something a bit more general than GR spacetimes as spacetimes. But yeah. Anyway, the point of this is going to be that I think we have good reasons to expect that even if that happens, we look at the somewhat more general family of spacetimes, the fundamental structures of quantum gravity are going to be different, and they're going to not look like those sort of things. And therefore, in that sense, you know, spacetime, GR spacetime, or something like GR spacetime is going to be contingent. And the second point, sure, so if you have a pendulum and you describe it classically, and then you discover, oh no, actually, you know, we should be better physicists, it's a quantum system, strictly speaking, you know, the states are a little bit different, there should be some quantum corrections, and the classical theory I had beforehand is only just a very good approximation at some scales. If I accept that, when I look at the fundamental theory that's now describing the pendulum, I see that according to this theory, it could have, you know, behaved very differently in non-pendulum-like ways, maybe with very low probability, what have you, or something like that. But it's possible that it acts macroscopically non-pendulum-like. And I mean, this is the reason why, you know, the classical electromagnetic fields of Maxwell's theory have been replaced by quantum fields, because in fact, even though classical magnetic EM fields are very good approximations for many purposes at, you know, many scales, nevertheless, sometimes what's actually there exhibits quantum effects that cannot be captured by Maxwell's theory. So, and then we replace it with a more fundamental theory. We look at quantum electrodynamics and we see now that theory tells us actually the physical systems we're looking at here could have behaved in ways which are different from classical. You know, so the classical electromagnetic field is a contingently obtaining classical approximation.
Baptiste has a brief follow-up.
Yes, please.
Yeah, just to thank you, Carlo and Niels. I think it's quite interesting. Just to make the point, I think what we are really after isn't really like GR spacetime as described by GR, as Chris said. I think one point to mention is you could have a very relaxed definition of spacetime as what's measured by words and clocks, something like that. You stay neutral, but what's spacetime at all? And you just say it could have been the case that we would be living in a world where there would have been nothing to be recorded by words and clocks. So I guess you can give a story about that without taking a view about what space-time is supposed to be, or I guess that's what I was after, what we were after in a very narrow way.
Thank you. That's a good point, yes. So rather than taking GR as a vantage point, we take some sort of operational theory about space-time in terms of clocks and rods, and say that
Does it need to be continuous, the space-time?
Sorry?
Does space-time need to be continuous?
So if we take GR as a starting point, of course.
In your operationalist one?
In the operationalist view,
That seems to be the crucial question, right?
I think it's more like, do you know the concept of phenomenal spacetime from Nick Huggett has? I mean, it's more like a very broad notion. Well, it could have been the case that there will be any concept of spacetime that would have been that we could have applied to this world.
so it's not as if you have a manifold and a metric or something like that as your mathematical representation of spacetime. It's more like you define there to be spacetime if you have rods and clocks in the theory, which may be continuum or not, and which are those things which pick up spatial distances or temporal durations or something like that. And the idea would then be you should expect that if you go to quantum gravity now, there will be some models of these theories of quantum gravity where you do not have clocks and rods like that.
Could you not generalize to Lorentzian geometries and
That would be one way, yes. That would be one way to sort of generalize, relax the idea of it's not just GR, it's like Lorentzian spacetimes. Yes, yes.
Okay, we've got 3 questions left, and so maybe we can pick up the pace a little bit. Lorenzo.
Yes, so I agree with what has been said by Niels and others, that we should be more specific about what we mean by space-time and by matter. It seems to me that you are very, very restrictive about what you mean by space-time, but incredibly liberal about what you mean by matter. And this is what bugs me the most. It seems to me that
Okay.
what we should count as matter is something that is relatively similar to particles or to a charged fluid in GR or a mass density in GRW, something stuffy, something that could fuse together to make a table or a planet or something like that. And if you're looking at a causal set and you say, oh, it looks like matter, quasi-matter, I have the impression that we're talking
Okay.
cross purposes.
Good. Yes. So thank you very much. The question about space-time has already come up. So as I said, I'm perfectly, happy to relax that and be less restrictive about that. I just don't want to relax it beyond recognition. I think as long as the relaxation remains reasonable, maybe to Lorentzian geometries or maybe to some sort of operationalist understanding, it's generally, nevertheless, we're going to end up with the thesis that space-time is contingent. And as for matter, I didn't mean at all to sort of endorse a particular conceptualization of matter at all. As a matter of fact, in the slide on relationalism, I meant to ask the question, what do we mean by matter? And this seems to become relevant if, precisely in the debate there, what do we mean by matter? Should we be so liberal as to count anything non-space-time-like as matter, in which case that might be give an unfair advantage to the relationalist. So presumably we will want to sort of narrow it down a bit. The question is, it's not so obvious just how to do that. It seems clear that we should not do it the way Descartes did it, by identifying matter as that which essentially has spatial extension, because then we tie it to space, and that seems, if you want to be a relationalist, maybe not the best way to go about it. But I completely agree. We need a reasonable conceptualization of matter. I certainly did not offer that. Yeah.
Thanks.
Tim.
Thank you. Well, you just sort of answered the question I wanted to ask, but I have a different question as well, which is whether you think that we do face a sort of specific type of problem of underdetermination as far as the model space that we allow as physical or as physical possibilities is concerned. Because that may be one reason why we would want to take that naturalistic notion of possibility a bit less seriously, ontologically speaking. Because you can always come up with an alternative theory where you just rule out certain models by fiat, basically, by, I don't know, depending on your theory, by ruling out certain initial conditions just as a matter of an additional law or whatever. And of course you can say, well, it's very unnatural and we have something like theoretical virtues. But then it's very hard to argue that these are really things that track truth out there.
Yeah, good. Yeah, no, that is an excellent question. And the question, I take it, that was also contained in Niels's comments when he sort of made the point that, naturalistic methodology is actually a much more subtle and complicated sort of business to try and figure out what exactly really are fundamentally the models we have here. I completely agree that this is a highly non-trivial thing. And maybe, one point where philosophers tend to be a little bit simplistic. So I'm not offering the ultimate resolution of that point. As a naturalist, I want to pay attention to the ways physicists impose additional conditions or deem something as actual real models of a theory and others not, without sort of compromising my independence as a philosopher. I sort of maintain the right to come in and say, like, well, let's not rule out those models just yet because, but nevertheless be in close interaction with the actual science to negotiate that. And you're right, I mean, that process is far from over, and it's logically possible that once that process has come to completion in quantum gravity, that we end up with a theory that is necessarily spatiotemporal. That's a logical possibility. It seems it's a remote possibility now, a sort of scientific possibility, given the current state of the field as I judge it. But yes, and this is something I accept, and this is also something that came up with Niels's comments. I accept that what I do, my metaphysics, is fallible, just as the science is fallible with which I engage. So, yeah, I'm hesitant to make any sort of final, fundamental metaphysics claims here, for exactly the sort of reasons that I think it was point C that Niels raised, that we should be careful here. Maybe what these theories are, we're not really at rock bottom, and there's all sorts of other more fundamental theories and so on and so forth. Absolutely possible, and absolutely possible that any of the lessons I'm drawing might then be obsolete. And to speak with Kerry Mackenzie, it's absolutely possible that my metaphysical interpretations, as I go to more and more fundamental levels, may not sort of converge onto some sort of metaphysics. It might be wildly oscillating between very different perspectives. I don't see any way around that at the end of the day. That's a risk I take, and maybe my work will be completely obsolete in 10 years when we have a completely different looking final theory of quantum gravity.
Okay, Klaus, last question.
Yeah, thank you. This is about the argument for the thesis, the main thesis, and you basically rejected objections against it, but I'm wondering what is the positive support for the thesis? So there's a burden of proof issue here. And I mean, one way of thinking is as follows. I mean, you have a mismatch of possibilities, right? There's the high-level theory, the fundamental theory, and I mean, this one has slightly different possibilities than that one, and this is the reason why then there's this contingency. But I mean, if you think about this mismatch, so why do you prioritize the possibilities at that level here? An argument, I mean, has to be given for that. And I think now it depends very much on the relation that you have here. I mean, sometimes I can imagine a relation, for instance, I mean, if this is only an approximation, right, and we think this is the fully established theory, then you can say, okay, I mean, who cares about the possibilities that we have in Newtonian theory, because we know it's an approximation anyway. But there might be other situations, maybe if there is some kind of grounding or so, where we might want to give priority to the possibilities at that level. I mean, there's an interesting analogy from philosophy of mind, where many people say, I mean, there's mind and there's physical states, and where many people say the level where we evaluate counterfactuals is the level of belief states and mental states. So here we are talking about these kind of possibilities, and that's what we care about, not the ground level. So if that's the case, maybe, I mean, we can say we have to prioritize the possibilities at that level, if we are not at that level.
Mm-hmm. Good. Yeah. No, that's a good question. It does. The project does prioritize the possibilities at the more fundamental level. You're quite right about that. And the idea for that is exactly as you pointed out, because it's supposed to be a relation analogous to the relation we have in other cases of physical theories, where GR is more fundamental than Newtonian gravitational theory in the sense that it's a better theory, it's closer to the truth, it's superior in the sense that we can explain why Newtonian gravitational theory was as good an approximation as it was in those domains where it was such an approximation, and we can moreover explain things where Newtonian gravitational theory went wrong. We can explain the advancement of the perihelion of Mercury, which Newton couldn't with the new theory. So that's why we take more seriously the models of GR than those of Newtonian gravitational theory. And this is supposed to be the same sort of move. The fundamental theory is supposed to give us the more physically serious and relevant possibilities, because it's going to correct some of the things GR does. It's going to explain why GR is as good as it is at the scales at which it's very successful. So we should be able to derive, the GPS corrections and the gravitational wave solutions, and all these things should come out of the fundamental theory. And moreover, it should give us an account of the physics of black holes and the very early universe, something where we believe GR is actually not going to be true anymore. So in that sense, that's supposed to be the justification for taking the more fundamental possibilities seriously, but you're quite right. So there is an asymmetry, and we assume that, and that's the argument for it. I'm not sure whether...
I mean, you're talking about grounding in other relationships, and sometimes, there's not this correction for the higher level theory, and then
that's true.
It's a bit different, maybe.
Yes, but we do think that there are going to be corrections like that, in the sense that there is.
Then I agree.
The more fundamental theory is asymmetrically better than the less fundamental theory. But you're right, it's a point that has to be made. It's not a priori obvious that this is the way it should go, absolutely.
Okay, let's thank Chris.
Thank you very much.